In the last video, we talked about specific heat capacity, and we talked about the formula where Q, the quantity of heat transferred, is equal to the mass of the sample times the specific heat capacity times the change in temperature. Q is equal to mc delta T. That's all well and good as long as you're heating up water or cooling down water, but what about change of state? Change of state becomes a little bit more complicated if we're going from solid, where those particles are kind of bound together, to more liquid, where they're tumbling but still tucked together, to a gas, where they're kind of floating around freely. A different amount of energy is involved than just heating it up. The other thing that's kind of weird is that when a substance is changing state, it doesn't change temperature, right? So there's no change in temperature. When you're warming water, of course, it's changing temperature, but when you're melting ice, it stays at the same temperature until it's melted. When you're boiling a pot of water, it stays at the same temperature until it's evaporated. So we're looking at something slightly different, and this is called the specific latent heat. So it's not the specific heat capacity, it's the specific latent heat. And so it's the amount of energy required to change the state of 1 kilogram of a substance, but there's no change in temperature involved. So the energy required to melt a solid to a liquid is called the latent heat of fusion. Why fusion? I don't know, something about melting is fusion. But latent heat of fusion is the amount of energy required to transform 1 kilogram from solid to a liquid. And the latent heat of vaporization is the amount of energy required to evaporate, really, to take 1 kilogram of a substance and turn it from a liquid into a vapor. The latent heat formulas are very similar to the specific heat capacity formulas, except again, there's no change in temperature involved, so it's even a little bit simpler. So our latent heat, for example, latent heat of fusion, QF, is equal to MLF, where LF is the latent heat of fusion and QF is the amount of heat required. And for latent heat of vaporization, QV is the amount of energy required to vaporize our sample, M is the mass, and LV is the latent heat of vaporization of the substance. Now, to give you an example, water has a latent heat of fusion of 333 kilojoules per kilogram, so that's 333,000 joules per kilogram to melt ice to water. The latent heat of vaporization of water is 20 to 55 kilojoules, so it's basically 2.2 megajoules. Okay, lots and lots of energy, 2.2 megajoules to vaporize 1 kilogram of water into water vapor. Compare that again to the specific heat capacity of water, which is only 4.19 kilojoules. So the amount of energy required to change state is quite a bit different. To give you an example, how much heat energy is required to raise 220 grams of ice from minus 18 degrees Celsius, say you pull an ice cube from the freezer, to room temperature, you let it sit at room temperature, so how much heat is it absorbing during that transition. Specific heat capacity of water, okay, is 4.19 kilojoules. As ice, it's actually lower. So the specific heat capacity of water in its solid state is 2.093 kilojoules per kilogram. And the latent heat of fusion is 333 kilojoules per kilogram. I guess all of those should have Kelvin after them. I apologize for that omission. So what's going to happen is we have ice warming to freezing, then we have it melting, and then we have it going from water at 0 degrees Celsius up to room temperature. So in the first step, we've got ice going from minus 18 to 0. Second step, we're melting it. And the third step, we're taking that water from 0 up to room temperature. So to solve the problem, the total amount of energy is going to be equal to the individual steps, so Q1 plus Q2 plus Q3. So we have the mass of ice times the specific heat capacity of ice times the change in temperature, plus the amount of energy required to melt it, plus the amount of energy mc delta T for liquid water. We can factor out the mass term. if you like, or you don't have to, you can just leave it in. But away we go, 0.22 kilograms times the specific heat capacity of ice, which is 2093 joules. The change in temperature is 0 minus 18, right? So that's going to be an increase of 18, plus the latent heat of fusion, plus the specific heat capacity of water, 4190 times 20, which is that second change in temperature. Okay, so remember that's all multiplied by the mass of our sample. So it's again, it's a pretty big number. Basically 100 kilojoules of energy just to take that ice cube, 220 gram ice cube, and melt it. Okay, now second example would be if I know how much energy I have and I add that to 100 grams of ice at minus 5 degrees C, what's the resulting state and temperature? Now this is a little bit different because I don't know what it's going to end up as, so I'm going to have to kind of do it a little bit more stepwise. So the first step is going to be warming up the ice, and I know it's going to be, if I plug in the formula, MC delta T, I get 1046.5 joules of energy to warm that ice cube up to freezing. To melt it, I'm going to, well, it's going to be 33.3 kilojoules to melt that little ice cube, so we still have lots of energy left over. So then I'm going to see if that water then reaches the boiling point. So how much, 100 degrees Celsius change in temperature, 100 gram sample size. That change in temperature, that energy MC delta T, is going to give me a value of 0.1 kilos times 4190 times the 100 degree temperature change, and that gives me this grand total of 41.9 kilojoules. So I'm still short of my total, so I'm going to start boiling off the water. So is there enough to boil off all of the water? So the latent heat of vaporization of my water sample is, again, it's 2255 kilojoules times my 0.1 kilograms. So I've got 225,000 joules, and my total so far is 301,000 joules. I'm still short of my 350,000 joules, so the rest is going to be heating up the water vapor. So again, I can use my value for specific heat capacity of steam, which I can look up, which is about 2 kilojoules. And so again, I just plug the values in. I know what the balance of energy is. I know that much energy is going to be warming up the steam. I know my steam is starting at 100 degrees Celsius, so I can solve for my final temperature, and I wind up with somewhere around 141.3 degrees Celsius. Okay. Now, one of the other neat things about latent heat is that it doesn't just take heat to melt ice to water, and it doesn't just take heat to evaporate water into steam. It works the other way as well. So if steam condenses to water, it releases that much heat. And if water freezes to ice, it releases that much heat. And this has all kinds of interesting consequences. One is the reason that clouds stay in the sky is that as water vapor from the air condenses into water droplets, every kilogram of water that's condensing into droplets releases over 2 megajoules of energy. That warms the air around the droplets, and that warm air rises. So clouds are actually lifting themselves up because the air in the cloud is warmer than the surrounding air because of all the heat released by the water vapor condensing into droplets. And tropical storms, big thunderclouds and so on, arise because the more heat there is, the more it rises, the more moist air it draws in, that condenses, that releases more heat, which rises, and you build these giant thunder clouds and giant tropical storms, all from this latent heat of vaporization being released back into the air by the water condensing. All right, I know this was short, but I hope it was useful, and I'm sure in class I'll be assigning some questions for you. So thanks for watching, and